going to record. Okay, let's see. No, sorry, it's not on. Yeah. Okay. So please remind me. Someone write me before this the lecture ends. Okay, when it ends. Okay. Let me see what's this. Can you see this chapter, concepts, electric field? What can you see, guys? Can you please tell me?
I see the slide, but there are some black things on the screen.
What's written on the slide?
Electric field lines, electrostatic.
Okay. So maybe the picture is not appearing.
Yeah.
Appearing well. Half black. How about now? Oh no, wait. How about now? Please say my name. It's good?
Yeah. And there's still بعد في محل فوق.
طيب اوكي. فوق هلا لانه انا كاميرا هلا مش الحال مش هيك؟
Yeah.
Okay, طيب. So we introduce this concept of the electric field, but very rapidly for a point source. Okay. So let's go back to this concept and try to see what is it actually? What does it mean? Okay. So if you recall in the problems, we were calculating the electric field at points in space. Okay. So basically, when the charge Q is when you have an object which is charged, the idea that I would like you to imagine is that it changes the space around it. Okay. And once this changes the space around it, then we need to describe this modification. Okay. What is this quantity who is going to describe the modification of the space around the charge? This quantity which quantifies the modification of space around the charge is called the electric field. Okay. I don't know if you guys have some notion of what we call general relativity. In general relativity, we have very similar concept, and that is, if you have an object with mass m, then this object will modify the space around it, which is represented in this picture that you see in this slide. Okay, you see this is Earth here, and it has a small dip, so it has small because it has small mass, so it will modify the space slightly around it, and this is the sun, and it will modify the space around it. So something similar happened, but not with the mass, but with the charge. And the way this curvature, this modification of space occurs is actually described by the electric field E. Okay, so the electric field describes the modification of the space around a given charge. That is the definition of electric field. And it's quite similar actually to gravitational field. You all know gravitational field. The weight equal to m multiplied by g, مظبوط? Okay, m multiplied by g. And here is roughly the same. The force F is equal to Q prime multiplied by E, and it's quite similar to mass multiplied by g. So G is the gravitational field, E is the electric field, M is the mass of the object, Q prime is the charge of the new object. Okay, so this is what the electric field means. This is a representation of the electric field. In order to represent the electric field, we need what we call electric field lines, and this is what we're going to discuss now. So it's really to visualize the electric field. In order to visualize the electric field, what we're going to do, we're going to introduce a new concept that's called a test charge. Okay, so a test charge is basically an imaginary charge. It's not real. Okay, but it will help us in drawing the electric field lines around a real charge. Okay, so this test charge has two major properties. One, the amplitude of this charge is infinitely small because it's an imaginary, so I can measure it's very small, and thus its effect on its surrounding is consequently very small. And second property, it is positive by definition. So it is a charge which is positive by definition, but has a very small amplitude. It has very small charge. Okay, so to give you an idea about what happened, so if you take the left-hand figure, the right-hand figure, these are what you see in blue. These are arrows indicating the electric field. Okay, and now if I put a real charge in this electric field, the real charge has its own electric field, and consequently it will come to modify the ambient electric field. But now if I would just want to measure this electric field, I don't want to perturb it. In this case, I'm going to put a test charge. This test charge, which is the left-hand figure, is so small, the amplitude is so small that it will not affect the surrounding electric field, and consequently, I will be able to measure the ambient electric field without actually perturbing it. Now, if you follow what happened to an A, B, and C, okay? Now, the question is, what's the electric field at point A? Okay, and I have a real charge, which is the blue charge, and it's charged negative. Well, since the real charge is negative and the test charge is positive, then it will be attracted to it. And thus, my electric field will point downward, will point towards this attraction, okay, or towards this motion of the test charge, okay? So, for this reason, the electric field will point towards the negative charge. Now, if I replace the negative charge by a positive charge, okay, then I ask to determine the electric field at this point here, at point P. Well, your reasoning would say, okay, you want to know the electric field at this point P, then I'm going to put a test charge at this point, okay, and see how its direction. And so what you see, the direction, since it will tend to go away from the positive charge because the test charge is positive and the real charge is positive, consequently my electric field will be upward. Okay? Now you tell me, okay, what's the difference between B and C? What you see is that in C, what we did is that we replaced this test charge by an actual real charge. Okay? If you replace it by real charge with Q0, okay, then the positive charges, okay, will be repelled, okay? So in this case, my distribution of charges in the real sphere will be different, okay? But since I want to measure the electric field at a point P of the real charge without any perturbation, then clearly you see that I need to reduce this Q0 to very small, that is the test charge, so that the initial distribution of charges is basically unmodified, okay? And for this shows you, the C shows you that if I replace my test charge with a real charge, okay, then this would lead to a modification of the charge distribution inside my real charge, and consequently whatever I'm going to measure is not going to be that of the charge, the initial charge, but that of the modified charge. Hence the importance of including a test charge. So if I have two charges as shown here, Q1 and Q2, okay, and I'll ask to determine the electric field at some point in space, then you say, okay, I'm going to put a test charge at this point in space, and the electric field caused by Q1 will be moving away from it because it's positive, and positive will repel each other. And the one which is from Q2, it will be pointing towards Q2, okay? Since plus and minus will attract each other, and this will going to be, E2 will be pointing towards Q2. And then when I add them up, I'm going to have E is equal to E1 plus E2, and this addition must be in a vector. So basically, you need to project and then add as we did for the force space. So these are the examples of electric field lines. What you see here, this is a positive charge on the left-hand side, okay? And if the idea is that whenever I put my test charge, then it will be moving away from it because test charge is positive, so it will move away from it like this, like that, like this. When I put a negative charge, it will move towards it in a straight line as shown here. So these field lines, they are basically going towards the negative charge and away from the positive charge. And now if I have positive and negative charges, then in general, the field lines must be away from the positive charge and towards the negative charge. This is another example, plus 2Q and minus Q. You see the electric field lines, and to the left, and this is to the right when you have the electric field lines for two positive charges. Okay. Just before I continue, I would like to share with you this website, which is really nice. Yes, you share this one. Share here. Okay, and let me see if I can. Okay, so this is the charge. Okay, this is the point source. If I draw, if I display the field lines, these are the field lines. Okay, I hope you can see it. Can you see it, guys? Yes, okay, perfect. Okay, so now if I add a dipole, so plus charge and minus charge, you can see these are the magnetic field lines. Okay, but I'm unable to make it bigger, although I should be able to make it bigger. Okay, so these are examples. Okay, if I have a quadrupole, this is the electric field lines for quadrupole. Okay, now what happened to test charges? Let me go back to a dipole, and let's see what will happen to test charges, not real charges. Okay, so display particles. So and then go stop go. So what you can see is that the test charges go away from the positive charge and towards the negative charge. Okay, but you can see display particles, forces, so velocities, that's better. So as you can guess, I hope, this is the positive charge because what you see, these small dot points, these are the test charge particles. Okay, so they will be going away from it. And as you can see, it will be going towards the negative charge. And these are our test charge particles. Of course, I can complicate things, but this is not what I want to. And the field lines that the lines they will take of these test charge particles is described by what we call the field lines. So basically, on the average, this is what can happen here. They will go from one point to the other, from the plus to the minus. Okay.